Hydrocarbon are the compounds consist of only carbon and hydrogen atoms. But don't let their simplicity fool you. They play a major role in our everyday life. Take LPG, CNG and LNG for example. Liquefied petroleum gas is commonly used as a clean burning domestic fuel. CNG or compressed natural gas powers vehicles with lower pollution levels, and liquefied natural gas is gaining attention as an efficient energy source. Other hydrocarbon power our daily activities too. Petrol, diesel and kerosene derived from the fractional distillation of petroleum are the backbone of transportation and home energy needs. Coal gas obtained from destructive distillation of coals also play a role. But hydrocarbons aren't just fuels. They are the building blocks of modern materials, polymers like polythene, polypropylene. They are also the key ingredient for points, dyes and even life-saving drugs. In this unit, we will uncover the fascinating world of hydrocarbon and their types. So, without any further ado, I welcome everyone to my YouTube channel where I explain the chapter from CBSE Class 11, Chemistry. So, to get the notification, don't forget to subscribe. Alkanes are the simplest hydrocarbons consisting of carbon-carbon single bonds. These are saturated, meaning they have the maximum number of hydrogen atoms attached to their carbon backbone. Methane, the first member of their family, is found in coal mines and marshy areas. Now imagine replacing one hydrogen atom in methane with another carbon atom bonded to the 3 hydrogen. What do you get? Ethane with a molecular formula C2H6. By continuing the process, replacing the one hydrogen atom with a CH3 group, you can theoretically construct an entire family of alkanes. These compounds follow the general formula CnH2n plus 2. Where n represents the number of carbon atoms. Structurally, methane adopts a tetrahedral geometry as explained by VSEPR theory. Each carbon-hydrogen bond has an angle of 109.5 degrees, creating a symmetrical 3-dimensional structure. The naming and structure of alkanes can be understood through examples. Methane, ethane and propane have only one structure each, but starting with butane C4H10, we encountered isomers. Now it's your turn. Try writing the structures and IUPAC names of all possible isomers of C6H14. Pause the video and give a try. Alkanes are primarily derived from petroleum and natural gas. But did you know they can also be prepared using specific chemical reactions? Unsaturated hydrocarbons such as alkenes and alkanes can be converted to alkanes through a process called hydrogenation. In this reaction, dihydrogen gas adds to the unsaturated hydrocarbon in the presence of finely divided catalysts like platinum, palladium or nickel. For example, ethene reacts with hydrogen to form ethane. Similarly, propane undergoes hydrogenation forms propane. These catalysts help to break the hydrogen-hydrogen bond, making the reaction possible. Alkanes can also be prepared from alkyl halides in 2 ways. Reduction with zinc and dilute HCl. Alkyl halide react with zinc and HCl to form alkanes. For instance, chloromethane react to form methane. Woods reaction. In this reaction, 2 alkyl halide molecules react with sodium metal in dry ether solution to form a higher alkane. For example, bromomethane produces ethane and bromoethane forms butane. Alkanes can also be prepared from carboxylic acid using 2 methods. Number 1 is decarbolization. Sodium salt of carboxylic acid when heated with sodium lime gives alkanes with one less carbon atom. For example, CH3COONA plus NaOH gives CH4 plus Na2CO3. Kolb's electrolytic method. In this method, an aqueous solution of sodium or potassium salt of carboxylic acid is electrolyzed to produce an alkane with an even number of carbon atoms. For example, 2CH3COO negative Na plus 2H2O gives C2H6 plus 2CO2 plus H2 plus 2NaOH. Methane cannot be prepared using this method. Can you guess why? Alkenes are nonpolar molecules with weak van der Waals forces. At room temperature, smaller alkanes are gases, medium alkanes are liquids and larger ones are solids. They are insoluble in water but dissolve in nonpolar solvent. Boiling point increases with chain length but decreases with branching due to weaker intermolecular forces. For example, pentane has a higher boiling point than 2-methyl butane. Under UV light, alkanes react with halogens. For example, methane reacts with chlorine to form chloroethane. This involves initiation or radical formation, propagation or reaction of radicals, and termination or radical combination. This is called a substitution reaction. Alkanes bond completely in oxygen to produce carbon dioxide, water and energy. Limited oxygen lead to carbon black. Alkane oxidizes to alcohol, aldehydes or acid under specific catalyst. For example, tertiary alkanes oxidize to alcohol with KMNO4. Linear alkanes form branched alkanes with AlCl3, while long chain alkanes form aromatic compounds like benzene under heat and pressure. Alkanes break into smaller hydrocarbon during pyrolysis, useful in petroleum refining. In steam reforming, methane reacts with steam to form hydrogen and carbon monoxide. Alkanes have carbon-carbon sigma bonds, allowing free rotation around the carbon-carbon single bond, resulting in different conformation. In ethane, two extreme conformations exist: eclipsed where hydrogen are closest and staggered where they are further apart. The staggered conformation is more stable due to less torsional strain. Rotation around the carbon-carbon bond in ethane is almost free, despite a small energy barrier. Next, let's see about alkenes. Alkenes are characterized by the presence of at least one carbon-carbon double bond. This double bond consists of a strong sigma bond formed by the head-on overlap of sp2 hybridized orbitals and a weaker pi bond, resulting from the sideway overlap of p orbitals. The pi bond's lower bond enthalpy makes alkenes more reactive than alkanes. The IUPAC naming system for alkenes follows a straightforward process. First, identify the longest carbon chain containing the double bond. Next, number the chain to give the double bond the lowest possible position. Finally, replace the suffix "an" with "ene". Alkenes exhibit two types of isomerism: structural isomerism and geometrical isomerism. Structural isomerism differ in arrangement of the carbon chain, while geometrical isomerism arises due to restricted rotation around the double bond. In cis isomerism, similar groups are on the same side, whereas in trans isomerism, they are on opposite sides. For example, cis-butene has both methyl groups on the same side, while trans-butene has them on opposite side. Now let's see the method to prepare alkenes. One common method for preparing alkene is the partial reduction of alkynes. When alkanes are treated with hydrogen gas in the presence of Linder's catalyst, cis alkanes are formed. For example, ethane can be reduced to ethene. Another method involves the dehydrohalogenation of alkyl halides. When alkyl halides are heated with alcoholic potassium hydroxide, a molecular hydrogen halide is eliminated, forming an alkene. This is an example of beta elimination reaction, where the hydrogen is removed from beta carbon, that is, the carbon adjacent to the one bonded to halogen. Vincenal dihalides, that is, the compounds with two halogen atoms on the adjacent carbon, can also be converted alkenes through dehalogenation. When treated with zinc metal, vincenal dihalide loses a molecule and forms an alkene. Alkenes can also be prepared by acidic dehydration of alcohols. When alcohols are heated with concentrated hydrochloric acid, a water molecule is eliminated, forming an alkene. This is another example of a beta elimination reaction. Just like alkenes, alkanes are unsaturated hydrocarbons. But what makes them different is the triple bond. This means they have even fewer hydrogen atoms than alkenes or alkanes. The general formula for alkanes is CnH2n-2. In IUPAC system, we name alkanes by replacing Ane with One. Alkanes exhibit different types of isomerism, mainly position and chain isomerism. Position isomerism occurs when the triple bond shifts position within the same carbon chain. Examples of position isomerism are but1-One and but2-One. Chain isomerism happens when the structure of the carbon chain itself changes. Pent1-One and pent2-One are examples of chain isomerism. Ethane can be prepared in two main ways. One is the industrial preparation from calcium carbide. Here the limestone is heated to form quicklime and the quicklime is heated with coke to form calcium carbide, and the calcium carbide reacts with water to produce ethane gas. Second is from vincenal dihalide. Benzenyl dihalides react with alcoholic potassium hydroxide undergoing dehydrohalogenation, forming an alkenyl halide. Further reaction with soda amide eliminates another alkyl halide molecules, giving ethane. Like alkanes and alkenes, alkynes also follow a trend in their physical properties. The first three alkanes are gases, the next few are liquids, and the higher alkynes are solids. Ethane has a distinct odor, but other alkanes are odorless. Alkanes are non-polar and insoluble in water, but they dissolve in organic solvents like benzene and ether. Their melting and boiling points increase with molecular mass. Now let's talk about how alkanes react chemically. Ethane reacts with sodium metal or soda amide, forming N-sodium acetaldehyde and releasing hydrogen gas. This reaction does not happen with alkanes or alkenes, proving that alkanes are more acidic. This reaction occurs because sp hybridized carbon have 50% S character, making them more electronegative. Pulling the CH bond, electrons closer and making hydrogen easy to lose a proton. Linear polymerization from polyacetylene, a conductive polymer used in electronics. Cyclic polymerization occurs when ethane is passed over red hot iron at 873 Kelvin. It forms benzene. Alkanes can add hydrogen, halogen or water due to their triple bond. For example, hydrogen is added to ethane to form ethene and it is called hydrogenation. Addition of bromine in ethane to form dibromoethene is an example of halogenation. Hydrogen halogen addition forms geminal dihalide, that is both halogen on the same carbon. Ethane reacts with water in presence of HGSO4 and sulfuric acid, forming acetaldehyde. The arenes are also called as aromatic hydrocarbons since most of them possess pleasant odor. Most of these compounds contain benzene ring, but there are examples of aromatic hydrocarbons which do not contain a benzene ring, but instead contain other highly unsaturated ring. Aromatic compounds which contain benzene ring are called as benzenoids, and those not containing a benzene ring are known as non-benzenoid. When any two hydrogen in benzene is replaced by two similar or different monovalent atoms or groups, three different position isomers are possible. If they are in the first and second or first and sixth, then while naming a prefix ortho is added. If they are located at the position 1 or 3 or 1 or 5, then meta is added as a suffix. Similarly, for position 1 or 4, para is added. The molecular formula of benzene indicates a high degree of unsaturation. Alkanes, alkenes and alkynes. On 1865 August, Calculi proposed the following structure for benzene, having cyclic arrangement of 6 carbon atoms with alternate single and double bonds and 1 hydrogen atom attached to each carbon atom. The limitation in Calculi's structure of benzene is later explained by resonance. The hybrid structure of benzene is represented by inserting a circle or dotted circle in hexagon. The circle represents the 6 electrons which are delocalized between the 6 carbon atoms of the benzene ring. All the 6 carbon atoms in benzene are sp2 hybridized. Aromaticity is the property of being aromatic and the compounds possessing characters such as planarity, complete delocalization of the pi electrons in the ring and those which obey Huckel's rule. The presence of 4n plus 2 pi electron in the ring, where n is an integer, is often referred to as Huckel's rule. Benzene is commercially isolated from coal tar. However, it may be prepared in laboratory by methods such as cyclic polymerization of ethane, which we learned earlier. Decarbonization of aromatic acid. Here, sodium salt of benzoic acid is heated with soda lime gives benzene. And reduction of phenol, where phenol is reduced to benzene by passing its vapor over heater zinc dust. Aromatic hydrocarbons are non-polar molecules and are usually colorless liquids or solid with the aromatic character. They are immiscible with water but are readily miscible with organic solvents. They burn with sooty flames. Arenes, unlike alkanes and alkenes, primarily undergo electrophilic substitution reaction, but can also participate in addition and oxidation reaction under special condition. Now let's see the most common reaction of arenes one by one. In nitration, benzene reacts with concentrated HNO3 plus H2SO4 to form nitrobenzene. The key electrophile here is the nitronium ion, which replaces a hydrogen atom on the benzene ring. In halogenation, benzene reacts with halogen like chlorine or bromine in the presence of a Lewis acid catalyst such as ferric chloride or ferric bromide or aluminum chloride. This reaction forms haloarenes like chlorobenzene. In sulfonation, the SO3H groups replace a hydrogen atom when benzene is treated with fuming sulfuric acid. This reaction is useful in production of detergents and dyes. Middlecraft alkylation, benzene reacts with alkyl halide in the presence of anhydrous aluminum chloride, forming alkyl benzene. For example, benzene plus methyl chloride gives toluene. In Middlecraft acylation reaction, alkyl halides or acid anhydrase react with benzene in the presence of aluminum chloride, forming acyl benzenes. This reaction is important in the synthesis of aromatic ketones. The reaction occurs in the three steps. First is generation of electrophile. For example, Cl2 plus AlCl3 gives Cl plus plus AlCl4 negative. Then the formation of a carbocation. The electrophile attaches to the benzene ring, forming a non-aromatic intermediate. And the final step is removal of proton. A base removes a proton, restoring benzene's aromatic nature. Hydrogenation occurs under high temperature and pressure with a nickel catalyst. Benzene gets hydrogenated to form cyclohexane. In the presence of UV light, 3 chlorine molecules add to benzene, forming benzene hexachloride. In combustion reaction, benzene bonds with a sooty flame, producing carbon dioxide and water. In monosubstituted benzene, the existing group directs incoming electrophiles to specific position. Electron donating groups like OH-CH3 activates the ring favoring ortho and para position. Electron withdrawing groups like NO2 and COOH deactivate the ring, directing substitution to the meta position. This effect is due to resonance and inductive influence. Benzene and fused ring hydrocarbons like naphthalene and benzoferine are carcinogenic, formed during incomplete combustion of coal, tobacco and petroleum. They enter the body, damaging DNA and causing cancer. The air toxicity makes them hazardous, requiring careful handling in industries and environmental monitoring. And that's a wrap on the chapter Hydrocarbon. I hope this video gave you the clarity and confidence you need to ace this topic. Remember, understanding hydrocarbon is all about connecting the dots and practicing the concepts step by step. So don't hesitate to revisit this video whenever you need a quick revision. If you found this video helpful, make sure to like, share and subscribe for more such content as comprehensive explanation. Also, let me know in comment which chapter or topic you would like me to cover next. Stay curious, keep learning and remember, knowledge is the key to unlocking your future. All the best for your exams and I will see you in the next video.